let me share with you some cases which we have been testing of 4 different boilers, and we performed the testing of the co-firing of the biomass with the hard coal, and we performed the biomass 100% combustion. And this 100% biomass combustion was performed in dedicated only biomass boilers. So we didn't use the coal boilers and gave 100% of the biomass. No, these 100% biomass boilers were specifically designed for biomass combustion. So in our opinion, the results should be quite representative. And also these boilers here, which were used for co-firing, were normal coal boilers, and we just implemented some extra biomass shares on 10% of the mass in this case, when it was the CFB, so circulating fluidized boiler, and something around 5% of the mass when it was the pulverized boiler combustion. And so we have 2 scenarios of co-firing for CFB and for pulverized, and 2 scenarios of combustion of 100% of biomass, also for fluidized bed and for pulverized bed. So we used different sorts of biomass: the wood chips, wood residues, pellets, sunflower husk, some agricultural residues, cereal crops, brewery grain. So different biomasses were used. And now let me draw your attention to some, in our opinion, important elements as the original parameters of the steam, of the live steam in these boilers. So when we observe these coal combustion units, the steam parameters were quite high. So we have something close to 14 megapascals of the live steam pressure in CFB and in pulverized also. And here, when you look at the biomass combustion, the parameters were worse, let's say. The pressure was lower. So here almost 14, and here almost a 10, and here it's even much lower than a 10. It's a little over 7.5. So a difference in these parameters give the influence on the energy efficiency. So generally, when energy efficiency of the plant depends on the parameters of the live steam. So when you look at this, generally, when we don't look at the fuel yet, we should expect the lower efficiency in the biomass only boilers comparing to the hard coal boilers, which were used for the co-firing. So these are the parameters which should be looked in the beginning, just to give some reference. And after that, we should only look at the biomass. Yes. Well, it's not like that the biomass combustion generally has such a small pressure of the live steam. We have another case, and I'm going to share this information with you also. That we have in Poland the biomass only biomass combustion unit. That was the world's first and the biggest 100% biomass unit based on a wood and agro biomass combustion. And here the steam parameters are higher. So you observe that it's almost like the 13 megapascals of the pressure of the live steam. And here it was, so it's comparable to the parameters of the live steam in this coal combustion and later on co-firing unit. So it's higher than that. So it's not like that in general that the biomass units gives the worst parameters of the live steam. You can encounter the big scale biomass combustion units, only biomass with the high parameters, and you can encounter smaller units for biomass combustion with the worst parameters. So if we really want to compare, if we really want to think about the biomass combustion, comparison to biomass co-firing, we should first look at the steam parameters of the both units. Yes, and so again, these 100% biomass units can be competitive in terms of efficiency when you compare it to the coal combustion. But on the other hand, it's not like that we can be better in the biomass combustion. When you look at the Drax power station in England, it was in 12 years ago the world's biggest biomass co-firing plant. So here the pressure is even higher than before. So it's like that we can go up with the parameters of the steam in biomass combustion, which results in higher efficiency. But at the same time, we can go even higher with the efficiency of the coal combustion, and later on the biomass co-firing. And this again gives a better efficiency. And here we don't talk about the biomass share. The biomass share was 10% here. But now the Drax has been fully converted into biomass combustion. The 100% combustion of biomass pellets are used here, and as far as I know, the parameters of the steam are still high. So the answer to the question, which gives the better efficiency, combustion or co-firing or 100% of biomass, it's really depending on the scale, and it's really depending on the size of the plant, and it's really depending also on the parameters of the live steam. And if you remember, the parameters of the live steam can change, and the parameters of the reheat can change. So in the same way, the efficiency can also change. And some results of the efficiency of the boiler of these 4 cases, which I showed you in the beginning, to pulverized and to CFB. They were evaluated and they are compared in the paper. If you want to get a little deeper in this case, if you want to dig a little more in the case, you can try to reach this paper. But I want to draw your attention to comparison. These two tables present the efficiency of electricity of the boiler efficiency, and the coal scenario is here with the letter C. We are at the pulverized fuel combustion, PF, PF, PF. In all these cases, means that we are in pulverized fuel combustion, and here we are the CFB. We are the CFB, and CFB and the coal. So these 2 first columns are pulverized fuel and CFB fuel and CFB boiler, and they are fired only with the coal. And the other group of data is just the co-firing with the 5% and 10%. The 5% was in the pulverized, so in this group of results, and 10% was in this group of the data. And you can observe that after some optimization, there was a very small loss in the efficiency, like the 1%. So we should expect more efficiency loss, but the efficiency loss was here you have not, like for example in this case 92, and we have 91.85. So like 0.20 of the percentage point was the decrease, and here almost the same, here a little lower, but generally we are on the level of 1.5% of the energy loss when we have been combusting 10% of the mass share in the biomass. And here, when you observe, it's also a little lower, but the differences are not so much. So generally, we observe the decreasing trend of the efficiency, but these are really small numbers. And this was...
If we have in mind your tables, and we have 2 situations, one pellets, the second one bales. Do you think that the influence on the efficiency will be the same of these two types of the biomass, or there will be any difference?
I would say it depends on the kind of scenario of co-firing, because what we observed when we have been co-firing the loose straw in the forms of the from the ballots, the loss of boiler efficiency was higher because the bigger pieces of the straw were not able to combust, and it was the scenario when the straw was just a cut from the big bale. The straw was just a cut, and it was blown inside of the combustion chamber. So in this case, the efficiency was, I would say, the lowest. But when we took the same straw and we made the biomass pellets, and we introduced the biomass pellets through the coal mill, so the biomass the same straw particles at this time were lower, and the combustion efficiency was higher, and in this case the boiler efficiency was bigger. So it depends, I would say, how you process the biomass before sending it to the boiler. The bigger pieces are, the lower efficiency. The highest efficiency in pulverized coal boiler is when you combust the pellets, but when you have the CFB, the size really doesn't matter. So the straw pieces or the pieces of the ballots or the pellets may be of the bigger size, and the combustion is generally better in the fluidized bed. So it depends on how actually you let's say introduce the biomass to the boiler. So it's depending on the scenario of the co-firing. So again, the answer is not so easy. The co-firing is quite a complicated case. It looks quite easy, but when you go very much into the details, sometimes the answers are not very clear. Okay, and the same as before, but it was the previous case was co-firing, and here you have the combustion of 100% of the biomass in CFB boiler, like the CFB here, and pulverized fuel is here. So again, maybe it's not very the changes are not very dramatic here, because you compare the combustion of one biomass to combustion of another biomass in all of these cases. But you can see that the sort of biomass, not the share, but the sort of biomass, if it's the pellet, or is it the agricultural residue, is it some food processing industry waste, it also influences the combustion efficiency, and it results in the boiler efficiency change. It's again plus minus 1%, only depending on the biomass sort, not on the biomass share, because we have 100% of the biomass in all of these cases, but depending on the biomass sort. So again, the answer to the question how the efficiency behaves, it also should take into consideration the kind of the biomass which is introduced. So the same boiler, the 100% biomass of this time, but different fuels and different and also different boiler outputs. So the levels of the boiler rating, it all influences the total efficiency. So to sum up, maybe some energy efficiency issues, we can outline that in general, the efficiency of electricity generation in the power plant is a function of different single unit efficiencies, let's say. So it's the efficiency of the boiler, the efficiency of the pipings between the boiler and the turbine. When we are sending the steam from the boiler to the turbine, the efficiency of the piping, also the in terms of the heat losses should be considered. The efficiency of the Clausius-Rankine of the power plant, so very general efficiency, also should be considered. The efficiency of the internal efficiency of the turbine, the mechanical efficiencies of the turbine and the electric generator, and the coefficient of the auxiliary electricity consumption. And some of these parameters are subject to change due to biomass co-firing. And as you know, this boiler efficiency for sure, the auxiliary electricity consumption for sure, but also something which can be forgotten when we talk about the biomass impact is the Clausius-Rankine efficiency. This Clausius-Rankine efficiency should be regarded in terms of the change of the steam parameters. As you remember from the previous slides, when we add the steam reheating to the basic steam cycle, we increase the total Clausius-Rankine efficiency due to the reheat. That's normal. We know it as the engineers. It happens. But the assumption is the same, that we reheat the steam. The efficiency gain assumption is that we must reheat the steam to the same level as the live steam. But as you observed before, sometimes we cannot do that when we add the biomass to the base fuel. And when you remember these graphs with the 15% of the biomass share in combusted blend, there were different temperatures of the reheated steam, and in some cases we were not able to keep the expected level of the reheated steam temperature. And in this case, we should expect the lowering of the Clausius-Rankine efficiency of the whole cycle. So that's again something which brings our total energy of efficiency of the power plant down. If we don't change the boiler load, and if we keep the steam parameters the same, if we manage to keep the steam parameters the same in terms of the live steam and the reheat steam, then we can forget about this Clausius-Rankine efficiency change. But if we cannot do that, we should consider that. Yes. So this may be summing up the efficiency issues. As you can see, it's very complicated thing. It's the influencing items are the numerals, the biomass source, the boiler load, the reheating steam parameters, the mass share, all this influence the efficiency of the electricity generation. And the answer to the question, which is more convenient, combustion or co-firing? The answer is not very easy. It depends on the case, on the size of the plant, of the parameters of the steam.